Dear students, today we will study commonly used terms in economics of power generation. First one is connected load. Any electrical appliance that consumes electrical energy is called as a load. It may be a lamp, it may be electric iron, it may be mixie at your home, refrigerator, exhaust fan, a grinder, a water heater, or a water pump. You consider anything, maybe a washing machine, which consumes electrical power is a electrical load. And every such load will be having certain rated capacity. That means when the rated voltage is applied to such electrical loads, they will consume a fixed amount of power. That is called as their rated capacity. Here, the connected load means the sum of continuous rating of the entire load consuming apparatus and outlets connected to the system. The connected load is the sum of the continuous rating of the entire load consuming apparatus and outlets connected to the system. Let us say, for example, we are having a lamp at our home, electric iron, water heater, and so on. These all will be having certain continuous rating. That means they can be made to operate continuously, consuming certain power. Such powers of all the loads, if we add to the outlets connected to the system. Outlets means a 3-pin socket or a 5-pin socket or any arrangement made to connect certain apparatus. That arrangement will be having some capacity. That means the arrangement may be made to supply a power to a load, say of 250 watt or 1 kilowatt or 2 kilowatt and so on. So if we add the capacities of outlets and the continuous rating of all the loads which may be connected to the system, then we get the total connected load. So connected load each device at consumer's terminal has its rated capacity. The connected load is the sum of rated capacities of entire load and outlets connected to the system. For example, say at a residence, number of lamps of 40 watt is 5. Number of fans of 80 watts is 4. Number of television set of 100 watt is 1. Ampere socket are 4 in number and 15 ampere socket are 2 in number. then connected load will be equal to 40 into 5 plus 80 into 4 plus 100 into 1 plus 5 into, assuming rated voltage as 230 and the power factor as unity, 5 into 230 into 1, and their number is 4, so into 4, plus 15 into 230 into 1 into 2, where 1 is once again unity power factor and 2 is number of sockets. Now the total power here is 40 into 5, 200, 80 into 4, 320, 100 into 1, 100, plus 5 into 4, 20, 20 into 230, 4600, plus 15 into 230 into 2, that will be 6900. Adding all these, we get 12,120 watts. So this becomes the connected load for the residence considered or for the premises considered. Second term is maximum demand. In this example, we have considered 40 watt lamps 5 in number, 80 watt fans 4 in number, a TV set of 100 watts 1 in number, 4 sockets of 5 ampere and 15 ampere 2 sockets. It is not necessary that all these appliances are put in service at a time, but only few of them may be put in service at a time. If I consider a 24 hours of time, say in that 24 hours of time, only 2 lamps of 40 watt, 2 fans of 80 watt, 2 sockets of 5 ampere and 1 socket of 15 ampere is in operation. And at other times, say less than these number of appliances are in operation. So the maximum demand will be calculated as sum of power consumed by 2 40 watt lamp, 2 80 watt fans, 2 5 ampere socket and 1 15 ampere socket. That is, the maximum demand will be 40 into 2 plus 80 into 2 plus 5 into 230 into 2 plus 15 into 230 into 1. We'll show that calculation later on. First, we'll write the definition of maximum demand. So the maximum demand of a consumer means the maximum power that the circuit is likely to draw at any time. In other words, the maximum demand of an installation or system is the greatest of all demands that have occurred during the specified period of time. Which may be monthly, yearly, or daily. It means that we may take a time span of one day to know what is the maximum demand on the system, or we can take a time of 1 month to know what is the maximum demand on the system, or we can take a year of time to know what is the maximum demand on the system. In last class we considered a graph which was explaining us demand at a station during the day. Let us consider that graph once again here. Now you can see here, in a day the maximum demand has only occurred at 8 o'clock in the evening, and that maximum demand is 140 kilowatt, and rest of the time the demand on the system or power drawn by the circuit is less than 140 kilowatt. Therefore, the daily maximum demand for the load considered here is 140 kilowatt, and this 140 kilowatt need not be consumed by a single load. This 140 kilowatt may be sum of various loads at the premises of a customer. In the above example, say in a day at a time two lamps of 40 watts, two fans of 80 watts, two sockets of 5 ampere and one socket of 15 ampere are put in service. And rest of the time less than these many appliances are connected. Then maximum demand is calculated as maximum demand equal to 40 into 2 plus 80 into 2 plus 2 into 5 into 230 into 1 plus 1 into 15 into 230 into 1. Forty into 2 80, 80 into 2 160, 230 into 10 2300 plus 15 into 230 3450. Altogether it will be 0 plus 0 0 0 plus 0 0 0 5 plus 0 5 5 plus 6 11 11 plus 8, 19, carry 1, 5, 5 plus 3, 8, 8 plus 1, 9, 3 plus 2, 5 watts. So maximum demand will be equal to 5990 watts. Next we'll take demand factor. This is third term to be defined. It is a ratio of maximum demand to connected load. So you can define the demand factor as the demand factor is the ratio of maximum demand to the connected load. Mathematically, it can be written as demand factor equal to maximum demand by connected load. Remember, if maximum demand becomes equal to connected load, that means at a time if all connected load is put in service, then the maximum demand will be equal to connected load. So connected load by connected load will become equal to 1. That means demand factor will become equal to 1. But practically it won't happen because no customer or no electricity consumer will connect his all load to the system at a time. So usually the demand factor value varies between 0.5 to 0.8. If maximum demand is equal to connected load, then demand factor will be equal to 1. But practically it won't happen usually maximum demand will be less than connected load. The demand factor generally lies between 0.5 to 0.8. Fourth term is diversity factor. To understand what is diversity factor, let us consider a power system X here, to which different consumer groups are connected. Say here is group A, here is group B, group C, group D, and group E. Now consumer A will be having certain maximum power, let us say that is PA max, and consumer B is having maximum power, that is PB max. Similarly, the maximum power demand of consumer C is PC max, PD max, and here it is PE max. Now in this group, all the consumers need not put their maximum load on the system at a time. What I'm saying? I'm saying on this system, all these consumers need not put their maximum load at a time, but only few consumers may put their maximum demand at a time and others will put their maximum demand at some other time. For understanding purpose, let us consider some numerical values here. Say P max is 100 kilowatt, say PMax is 100 kilowatt, PBmax is 80 kilowatt, PCmax is 50 kilowatt, PDmax is 120 kilowatt and Pmax is 150 kilowatt. I will define what is diversity factor. The maximum demand of all consumers of a group does not occur simultaneously. When considering the rated capacity of any equipment it is also known as group diversity factor. DF is always greater than 1. In the above example, if consumer A, D and E put their maximum load at a time with consumers B and C drawing consumers B and C drawing 40 kilowatt and 30 kilowatt respectively. Then maximum demand of wool is equal to 100 plus 120 plus 150 plus 40 plus 30 kilowatt. Whereas sum of individual maximum demand is is 500 kilowatt. Therefore, diversity factor becomes equal to 500 kilowatt. Therefore, diversity factor becomes equal to 500 kilowatt divided by 440 kilowatt, that is equal to 1.136. Next we will define peak diversity factor. The ratio of maximum demand of a consumer group to demand of consumer group at the time of system peak demand. To understand what is peak diversity factor, let us consider a 11 kV feeder here, to which 3 11 kV by 415 volt transformers are connected. Transformer 1, 2, 3. Say, to each of these transformers, loads L1, L2, L1 dash, L2 dash, L1 double dash, L2 double dash are connected. And say the maximum demand on transformer 1 during a specified duration of time is P1 max, for transformer 2 P2 max, and for transformer 3 it is P3 max. Now let us say the maximum demand on the 11 kV feeder is X. When the maximum demand on the feeder equal to X kilowatt occurs, then the peak diversity factor PDF for group 1 may be defined as P1 max divided by L1 plus L2. It means that when there is maximum demand of X kilowatt on the feeder of 11 kV, then group 1 consumers are consuming a power of L1 plus L2. So here in the denominator we are taking L1 plus L2. Because L1 plus L2 is the demand of consumer group 1 when there is a maximum demand of F. Because L1 plus L2 is maximum demand, because L1 plus L2 is demand of consumer group 1 when there is a maximum demand of X kilowatt on feeder. Same way we can calculate PDF2 and PDF3. PDF2, that means peak diversity factor for group 2 is equal to P2 max divided by L1 dash plus L2 dash, and PDF3 is P3 max divided by L1 double dash plus L2 double dash. So what are these denominators here? These are demands of group of consumer when there is maximum demand on feeder.